So I request Dr. Patel Sardar to introduce our today's speaker to all the participants.
Yes, sir. Thank you, sir. Good morning and warm welcome to all respected professors and participants for day third, session 7 of AICT Atal Sponsor Faculty Development Program on MEMS. It is my pleasure to introduce our today's eminent speaker, Dr. Suhas Mohite, sir. Dr. Suhas Mohite, sir, is a professor at College of Engineering, Pune. He has done B from Walchand College of Engineering, Sangli in 1988. He did his MTech from Indian Institute of Technology, Madras in 1990. He has done PhD from IISc Bangalore in 2008. He has also he has industrial experience as a graduate engineer in Bajaj Auto Limited, Pune, from 1st August 1988 to 22nd July 1989. He has also served as a senior engineer in Wipro Fluid Power Limited, Bangalore, from 10 February 1991 to 19 July 1991. He has published more than 40 papers in international conferences, 13 papers in national conferences, and he has more than 10 journal papers, publications, and several patents on his name. I welcome Dr. Suhas Mohite, sir, for our FDP, and I request Dr. Suhas Mohite, sir, to start this session. Hand over to Dr. Suhas Mohite, sir.
Thank you for that introduction.
Yeah,
Only thing is there is a small correction. I don't
yeah,
have any patents in my name. Shall we start? Shall I?
Yes, sir. Yes, sir. You can start. You can start. You can share your screen.
Yeah. Where do I get that? Because these three
Sir,
dots is
below,
not.
yeah. You can see the three
Yeah,
dots. You can just
but
put the cursor over
it has
there.
got a different menu, like change layout and those things are there.
No, sir, not three dot. Beside three dot, present now is there. Present
Okay.
now.
Yeah.
Yeah. Click on that present
From
now.
present now you can present, sir.
Yeah. From present now, click on present now and say
Entire
the
screen.
entire screen. Yeah.
Is my screen visible?
Not yet, sir.
No, sir. No, sir.
no, sir.
Yeah, it will be.
I think, sir, you have not clicked the present now. Your entire screen you click, and there is OK or something like that. Share or something like that. You can
Oh,
click on
share.
that. Yeah.
Share is there.
Uh-huh.
Share your entire screen. Okay.
Yeah.
But share is not getting initialized.
You can click
Cancel.
on that particular figure first of all, which entire screen is coming. Some figures are there. So you can click on that, then share
Yeah.
will be activated.
Yeah.
Yeah. Now it is in transition. Yeah, presentation is in transition. Correct.
Yes, sir.
Yeah, now
it
it is
is
visible.
right.
It is visible. It is visible.
Sir, full screen kara, sir.
Yeah.
Yes, sir. Now it is perfect. Perfect, sir.
So, good morning, all.
Good morning, sir.
I hope most of the participants have joined. So, the last 2 days, in fact, I had been to some of the presentations in past 2 days, and it has been a feast to listen to eminent speakers with the state of the art technology examples that they showcased. So I will be touching on to the basic aspects of MEMS, because in my opinion, many of the participants are new to this particular field, and they are from different backgrounds. So I have decided to, connect few dots from what they know, and then we will move on to what is new and to many of the participants. So mechatronics is something most of us are familiar with. So let us have a quick look at that, and then we will move to MEMS and nanotechnology, how the scaling takes place. The outline is going to be like, we will take a bird's eye view, and then we'll see how the scale of the things changes from meso, micro, and nano. And then we will just take a quick look at the history behind these developments, which dates back to 70 or 80 years. Then the important thing that is fundamental to the development of MEMS is microelectronics, from where the MEMS has evolved. And then it is the IC fabrication technology which is actually at the generic form to the MEMS. MEMS initiated from there. So initially it depended heavily on IC fabrication technology and the processes and the materials used there. And later on, now there are several other materials, as you came to know 2 days back from Professor Anand Suresh, who said that polymers and glass and several other new materials are being used in MEMS. So now MEMS have grown quite a lot, and therefore materials and processing also has now, which was earlier dependent heavily on IC fabrication technologies and the processes and materials related to that. But new materials and new processes have come in a big way with the development in MEMS. Then the fabrication also has been basically generically, it comes from the IC fabrication. Then we'll see some of the aspects of design and analysis of MEMS and packaging. And then we will take an overview of applications. And one application I would like to deal with in a little more detail, that is MEMS gyroscope or angular rate sensor. And then we'll see what are the challenges and possibilities for the new researchers in the field of MEMS. So mechatronics, which we are all familiar with, all the mechanical, electrical, electronics, instrumentation, control engineering, computer, even IT people are also familiar with these, because these days we talk about Internet of Things or Industrial Internet of Things, Industry 4.0, where there is a extensive use of sensors, collection of data and data analytics and interpretation. These things are being talked about in a big way these days. And you think of a thing and we talk about mounting sensors onto that, and several new areas are emerging with the integration of different technologies. So mechatronics has begun several decades back, and it has grown into the need of several sensors. And microelectromechanical systems is a miniaturization sort of, you can say, of that particular a meso-scaled mechatronics, that big devices that we see, which have got sensors, actuators, and controllers which control these devices. But essentially what goes into these is sensors play a very vital role, and need and development of various kinds of sensors has gone in a big way, and the development is taking place in the area of MEMS, where these devices are fabricated on a silicon wafer alongside the electronics. And the integration, unlike in mechatronics, you can see the different devices separately. In MEMS, the integration is very, very strong and very close. So it is difficult to, differentiate. The electronics and the mechanical devices are sitting pretty close on a substrate. And that is the beauty of MEMS that you can see here. This is apparently a integrated circuit chip, but it has got moving mechanical structures sitting inside it. and these structures, when acted upon by certain physical signals such as pressure, acceleration, rotation rate, or and things like that, they undergo deformations, which results into transduction. Various types of transduction principles are used in these devices, such as capacitive transduction, piezoelectric, piezoresistive, and so on and so forth, where the electrical signal is created, and that tiny electrical signal, uh, where the change in the capacitance could be of the order of pico, femto, or autofarad, which is extremely small, but immediately the electronics is sitting next to it, and therefore these devices are in some sense protected from the noise in the environment, because there is not a big gap between the sensor where the tiny signal is produced and the electronic circuits which carry out the immediate signal processing, such as uh, the amplification, the filtering, and similar similar processes on the signal processing circuits that are built in the vicinity with various kinds of operational amplifiers and devices. Then the sample and hold and all those circuits, which will be sitting very pretty close to the transducer, and therefore there is a little loss of signal, and there is little loss of scope for the noise to play a role there. Although the signal that is available is pretty small, but there is a amplification that takes place in the immediate vicinity alongside the electronics. So in MEMS, there is a strong integration of mechanical and electronic devices, and you can see several miniature devices are fabricated on. Those who are familiar, electronics people are familiar with CMOS circuits. They know that there are several capacitances that come into picture, and there are deliberately manufactured parallel plate capacitance or comb fingers that can be built using this silicon fabrication technology. Even inductors are possibly can be created. A simple cantilever beam or diaphragms can be fabricated on this silicon substrate, and various transducers can be realized. So, and in the end, you will have this particular packaged integrated circuit chip, which can sit onto a small board, which is on the tip of a finger. And you have energy harvester. For example, in this picture you can see an energy harvester. Here you can see another device uh, that is sitting inside the chip, and then you can see a gyro or an accelerometer or a pressure transducer that is subjected to that is sitting in a small packaged device, which is totally protected, and it can work into any kind of environment. And the next thing after mechatronics, we discuss MEMS. Just a small look at uh, uh, the technology, and then the nano electromechanical systems are also being talked about, and we hear quite a lot these days. So it's the scale of the things that is getting changed by almost 3 orders of magnitude, from meso, micro, and nano. So there is a 3 order magnitude shift in the scale that is being talked about, and there is a possibility that was, envisaged by Richard Feynman and Gordon Moore and likes 50 years back, 60 years back, and the technology is being realized in modern times. And we talk about nanoparticles of various sizes, the various kinds of surfaces and chemistry that goes into a variety of shapes that can be created, and different materials have emerged these days, such as graphene, carbon nanotube, and several types of polymers, and metallic particles and hydrogels, and several applications too have come up with the advent of these. And especially the field of medicine has undergone tremendous uh, change, and it is going to offer several things in the days to come with the various developments that are taking place. And this is how you can manipulate at various scales. So nanotechnology is the era of where 1 to 100 nanometer, that means this is the scale in which things are manipulated in nanotechnology, whereas in micro electromechanical systems, it is from fractional micron to several hundred micrometers is the range in which MEMS comes into picture, and whereas the mesoscale devices are in millimeter to meter scale, which we are all familiar with. So thus, I hope you have got that this is a millimeter, micrometer, and nanometer scales of the things that they function. And with these scales, in fact, you have several other significances that are attached to these changing scales of milli, micro, and nanoscale materials, because you have the response times scaling in the same order as that of milliseconds, microseconds, and nanoseconds, or the operating frequencies that we can use are in meso kilohertz, then megahertz, and gigahertz. So that is how things are also alongside scaling. When the physical dimensions undergo change, the time scales also undergo change. That is something you have to keep in mind, because the device response time also reduces or shrinks considerably by orders of magnitude. We used to have kilobyte memories, and megabyte, gigabyte, and terabyte memories are possible because of the shrinking length scales of these devices. So now let us move on to the MEMS and MEMS technology. So for past 2 days, you know that MEMS is micro and electromechanical systems, which are integrated systems. The functionalities are integrated. The components are exchanging signals across the boundaries of the domains: mechanical domain, electrical domain, fluid and thermal domain. 2 days back, you saw the thermoelectric tweezer. An example was given by Professor Anand Suresh. So various domains. In mechanical domain, you have structural, thermal, and fluids interacting with electrical uh, quantities such as capacitance or changes in capacitance, inductors, or resistance changes, which in turn are converted into some kind of sensors, and then electronics processes those signals for the purpose of analysis and then further actions and applications, uh, which is driven by these various levels from physical to electromechanical, then electronic, and then computational part if needed, that can come into picture, and data analytics. And that is how at various scales the applications are growing with the advent of this technology. The size, it takes a while for a new person to come to terms with the size of the devices that we are talking about. So these are some of the marvelous creations. Friends, mind well that you are all currently using these MEMS devices, and these devices are very much sitting in your mobile phone, which you are carrying in your pockets. I don't know whether you have ever wondered how small is the microphone and the speaker, micro speaker rather, that is there in your mobile phone, and what is the technology that goes into manufacturing of those microphones. So those are essentially MEMS microphones, which are produced on large scale with batch fabrication technology using silicon micro machining. The speakers too are being manufactured with this technology. Then you have what is known as a rotation rate sensor. As you tilt your mobile phone or turn your mobile phone, the screen flips from a portrait to landscape, and that is basically a sensor which senses this rotation or movement and responds to the change that is uh, experienced by the device. So that's why we call it a smartphone or smart device, because it responds to the environmental change. It can show you your blood pressure, it can show you your stress level. And I mean, mobile phone is one thing, but there are several other applications that are emerging with the mobile phone, such as it can monitor your blood pressure. It's all possible because of the sensors that are being fabricated at a miniature level, at a uh, affordable level, at a large scale, with the same technology that goes into the fabrication of electronic devices. So this is something that has to be kept in mind or borne in mind by mechanical engineers, that conventionally we use various mechanical manufacturing processes. However, MEMS devices essentially make use of additive and subtractive manufacturing and the processes that go into manufacturing of electronic circuits. So IC fabrication technology or the processes that are being used by MEMS fraternity. So this is another important thing. Not only that, the material in mechanical engineering, the conventional materials are various types of metals and metal alloys, steels, iron and aluminum, copper and so on and so forth. However, they are not amenable to the IC fabrication technology. So IC fabrication technology essentially with germanium or silicon wafers, it has emerged and it has developed and grown uh, and advanced. And therefore, there was a need to, when mechanical engineering tried to enter into this, these were the constraints and limitations, and therefore mechanical engineers, they adapted to this silicon as the mechanical material. Silicon was never talked about mechanical materials. However, silicon is being used as mechanical engineers, and that is how the emergence of MEMS has occurred. Micro electromechanical systems have got sensors, miniature sensors, micro actuators, microstructures, means devices, and microelectronics. So it's an integration, a very strong integration of sensors, actuators, electronics, and microstructures. Now, the sensors can be as small as possible, and functionally they do not have any issue. Whereas actuators can be micro or meso or large scale, because when you want to operate in physical world something huge, then you have to have big actuators. Miniature say actuators are also possible, especially they are suitable in medical applications. However, when you are wanting to do something in the meso world, then obviously the actuator part is going to be big. So this particular another important aspect has to be borne in mind. So you can have sensors as small as possible, but then it helps in several ways. You can have arrays of sensors that can be deployed uh, to collect several data of different kind, and a variety of sensors also can be deployed in a certain application to acquire a variety of different signals such as temperature, pressure, flow, uh, and light intensity, acceleration, rotations, etc., etc. Several parameters can be sensed by a variety of sensors, and you can have array of similar or a variety of sensors deployed in a certain application. And essentially what is needed is sensor and the electronics needs to be a miniature. Earlier what happened is electronics scaled down several orders of magnitude since the advent of first transistor, which was of the size of few millimeters, and later on it became of micron, and these days it is at the nano scale. However, the mechanical devices did not scale down that much, but MEMS technology did that particular thing by integrating itself with the IC fabrication technology. So an important factor in the progress of miniaturization technologies is MEMS and mechatronics. Micromechatronics, it can be called as micromechatronics. MEMS consists of integral micromechanical and microelectronic elements fabricated by established semiconductor processing technology. This is another important. Various types of sensors such as pressure sensors, acceleration sensors, gyroscopes, microphones, and so on and so forth. Actuators of a different kind, linear and rotary actuators, miniature actuators we are talking here, valves. There are drug delivery systems where there are miniature pumps that can be mounted onto human body, or the devices can be worn on the wrist or any part of the body. So wearable devices have come in, where the drug delivery system is there, where there is a tiny pump, a miniature pump, and there is uh, a tank that can hold a microgram of medicines. So then there are tweezers to manipulate things at micro level. The one of thermoelectric tweezer that you saw the other day. There are varieties of motors, gears, gear trains, turbines, nozzles, and pumps that are fabricated as actuators using MEMS technology. It's a critical technology in the field such as aerospace has got huge applications, automotive applications, biomedical and communication industries. Commercial applications of the MEMS include microfluidics and then manipulators for implantable drug dispensers, navigation gyros for aerospace use, and magnetic and optical storage and switching devices, which are very popular, and radio frequency MEMS also you might have heard about, and displays for the uh, projectors and information technology. The advent of MEMS goes back, or the nanotechnology that we are talking today, and you must have heard the famous talk given by Richard Feynman, where he proposed the possibility of ultra miniaturization or the size reduction by 3 orders or more than 3 orders of magnitude in mechanical systems, as well as miniaturization of computers to the levels involving the manipulation of atoms. You might have heard about single electron device also. So that means a switch can, how small a switch can be, it can go down to a level of presence or absence of an electron. So such is the possibility that one can think about when things get miniaturizing, the switch can be represented by a presence and absence of electron. Although we have now a very nanoscaled transistors available these days with 10 nanometer technology, while these possibilities were envisaged, these possibilities were envisaged by these visionaries around 70 years back. While these ideas were undoubtedly prophetic in those days, the technique envisaged of three-dimensional machines iteratively making ever smaller and smaller versions, one machine making another machine smaller than itself, and so on and so forth. That is how the idea put forth by Richard Feynman, and it was unlikely ever to be practical, a point acknowledged by Feynman himself after revising the concept in 1983. Nano-electromechanical systems, or NEMS, is the next logical miniaturization step from MEMS and is used to describe devices integrating electrical and mechanical functionality on nanoscale. Often employing the 2010 Nobel Physics Prize winning material graphene. You must have heard about this material graphene, which is a landmark development in the field of nanotechnology. And this material is finding a lot of applications. It has got properties that are extremely beneficial. And this is atomic force microscopy is also developed here. And it has got several applications because you can manipulate at that scale. Currently, the most significant technology for the fabrication of three-dimensional MEMS microstructures are bulk micromachining and surface micromachining. Besides that, there are other processes such as LIGA and EDM and substrate bonding, etc. NEMS systems rely on two basic principles of fabrication: photo and electron beam lithography. Photolithography or electron beam lithography, and molecular self-assembly, because nanotechnology is a level where you manipulate molecules, and molecules have got dimensions of fractional nanometers or in angstroms. And with the these atomic force microscopy, you can manipulate these uh, particles at nanoscales. So this is a new development that is expected to, and it is taking place in a big way. Now let us have a fresh look at the scale of the things that is occurring in the nature and that are developed by humans. This scale starts at 1 centimeter and ends at 1 angstrom. From centimeter to angstrom are the two extremes of this particular scale. At the centimeter scale or millimeter scale, what you find is the ants, which are approximately 5 millimeters, and then dust mites, which are 200 micrometer, which is 0.2 millimeter, fractional millimeter, followed by fly ash, which is 10 to 20 micrometer. Human hair range from 60 to 120 or 100 to 200 also. If thick hair are there, you can have the human hair thickness is 200 micrometer. We need to know the scale of few things so that we can relate. Otherwise, numbers are do not make sense unless we relate them to something physical. Red blood cells are 7 to 8 micrometer in size, and you have 10 nanometer ATP molecules which can be synthesized and which are available in nature. So those can be even synthesized manually in laboratories. Then you have DNAs and atoms which have got these molecules, and this is the atoms of silicon spacing tens of nanometer. See, there is a huge gap between these atoms. I will take a pause here. You have to watch this particular picture where we are seeing atoms, and the atoms have got a huge void in between them. Atoms of silicons are being seen, and there are tenths of nanometer. That means the size of atom is a fractional nanometer, but the gap between the atoms is several times their own size in solids, in silicon. Richard Feynman has said that there is plenty of room at the bottom. This is the room that he was referring to. That means the atoms, or you all of you probably must be remembering Rutherford's experiment with alpha particles, I suppose, where he found that when he sent the high velocity alpha particles through the foil, gold foil, several particles, large number of particles, they went straight. What it meant was that there was a void that allowed the particles, which are helium atom particles, passing through gold foil, a thin gold foil, and most of the particles were found to go straight. What it means is that there was a void. So that means something that is not visible to our eyes doesn't mean that it doesn't exist. There exists a huge gap in solids, and that particular gap between the, I hope you are getting. Hello?
Yes, sir, perfectly. Yeah.
Yeah. See, I'm trying to, make you think on your own about what is there in between atoms. I mean, when we say that there are atoms, the structure of atom also we have all studied. There is a nucleus and there are orbits. But what is there in between the nucleus and the orbits? There is a gap. There is a gap there, right? So that means there is void actually, even within an atom. Between atoms there is a huge void, between molecules there is a huge void, and among molecules also. For example, if you take air molecules, mechanical engineers are aware of one term called as what is that, mean free path of gas molecules or air molecules. it is 70 nanometers. What is the meaning of mean free path? It is in kinetic theory of gases, the molecules of gas are continuously in random motion, and they collide with one another, and this average distance of collision is 70 nanometers. Average distance of collision is 70 nanometers. Now think about a oxygen molecule. The radius of oxygen molecule may be a fractional nanometer, or nitrogen, a fractional nanometer, because it is few angstroms, 2, 3, 4 angstroms, which is fractional nanometer. And these molecules are there present in the air that is around us, within us, where we are ourselves immersed in this particular air. But these molecules are separated at that scale. They are separated on an average a distance of almost 100 times their own size. For example, if 7 angstrom is the radius, let us assume that 7 angstrom is the radius of a particular gas molecule, which is 0.7 nanometer, and the average distance between the collision of two molecules is 70 nanometers, which is 100 times. That means there is a gap of 100 molecules in between two molecules on an average in a gas, right? So there is plenty of room at the bottom. And even if you take the case of solid, as I told you the example of Rutherford's experiment, where he impinged these helium nuclei over a gold foil, and several alpha particles went straight, meaning that they found a void there. So this particular aspect has to be kept in mind, that we as a human, we have certain limitations of vision, and but the thought doesn't have a limitation, and that is the difference between us and those visionaries that I referred to. Richard Feynman had this particular vision that when the structure of an atom molecule was conceived, the concept was evolved, then they thought about the scale and the size of these things, and then the size that gave rise to the thought process of what is the gap between these two, and can we manipulate those devices. Even those things were not possible at physical level in those times, but at the mental level they could envisage this, at the mental level they could imagine this. So that is how you can, there is a thought process that can start, even if you give a small attention to this particular fact of what is the gap between the atoms. Now we have these man-made things which are head of a pin, and then micro electromechanical devices that are fabricated on silicon wafer, which are tiny devices like this. Then you have red blood cells, which are here for comparison with these gears. These blood cells are of this size, and the devices that can be fabricated. So the possibilities, you have to first of all come to terms with that these possibilities are there, and that is what the technology, MEMS and nanotechnology, that is being talked about. The fabrication of a combined nanoscale building blocks to make a useful device. For example, photosynthesis reaction center with the integral semiconductor storage. So, this is how tiny building blocks can be. The way a transistor is a basic building block, similar to that, a transistor is a basic building block. Similarly, molecules are the basic building blocks in nanotechnology. Remember, a transistor is a basic building block in microelectronics. On the similar lines, you have molecules as the basic building blocks in nanotechnology. So that once that fact is understood and digested, then it is possible to imagine further. These are the carbon nanotubes. then you have these atoms of iron. 48 atoms of iron are being arranged in the form of a coral here on the copper surface, positioned one at a time. An STP tip, a scanning tunneling microscope is used. Scanning tunneling microscope is used, and its tip has carried these iron atoms, and they have been arranged in this. So that means nanotechnology is about manipulating atoms and molecules. This technology was envisaged 70 years back. It has become practicable today, and it is opening new possibilities and being referred to as nanoscience, nanotechnology, nanoengineering, so on and so forth. But it is all about what we do at mesoscale, the kinds of assemblies that we do at mesoscales, the kind of assemblies that we do at micro level, and the kind of manipulations that we do at nano level. This is the scale of the things is changing. Most ideas remain the same. So thus, this is a historical background that we touched upon, and these visionaries, we must remember them, that there is a plenty of room at the top, at the bottom is what he said. It was a talk given in American Physical Society in Caltech in December 29th, 1959. Feynman described a process by which the ability to manipulate individual atoms and molecules might be developed using one set of precise tools to build and operate another proportionally smaller set, and so down to the needed scale. So this was a thought that was put forth way back. Another visionary is the number of transistors, as most of the electronics people are very familiar with this. On a chip will double every 2 years. In fact, the law got modified, and it took 18 months for the doubling of and the process is on. And this was said in 1965, and now it has been more than 50 years. The Intel founders' words Intel has kept the pace of over 40 years or 50 years rather, providing more functions on a chip at significantly lower cost per function. Now let us now get back to the manufacturing process and the materials that are used in making micro electromechanical systems. Now this is a familiar picture, one can say, in a foundry of mechanical engineering. So this is a silicon foundry where wafers are manufactured, where silicon is melted, and its bar shaped silicon is made available after solidification, which is called as ingot of silicon, and then it is sliced into wafers. So this is how actually the mechanical system, the mechanical foundry, that is at the beginning of the fabrication of wafer, which is a substrate for the electronics industry. So silicon wafers are essentially fabricated or manufactured in a wafer fabrication facility, similar to the melting of other metals. Now, these silicon metals in wafers are in turn undergo several processes such as polishing and sizing and cutting and so on and so forth. And silicon offers directional properties, and therefore there is, you can see a flat edge here to mark its directionality, because it has properties changing in different dimensions. So these are some of the processes that go into the fabrication of or manufacturing of wafers. So this is how the crystal growth, and then ingots, and then you have flat grinding, and then slicing of the wafers, and then wafers edge rounding, and then lapping of the several wafers, and etching of the wafers to remove the burr and things like that, polishing, and the wafer is available as a raw material for the electronic fabrication. So this is how wafer fabrication process in silicon that undergoes most of the mechanical processing goes behind making of a substrate silicon wafer, which is available in 4 inches, 6 inches, 8 inches, and 10 inches size, on which the circuits are laid down later by various IC processes. The IC fabrication processes, this is a quick look at uh, what processing the wafer undergoes. So since you have seen the wafer here, the wafer is the basic raw material that goes into fabrication of electronic components, integrated circuits that we call them, where doping is the first thing that took place, and you have the realization of the PN junction diode, and then PNP and NPN transistors, and then the transistors evolved into analog transistor and a digital transistor, and then the digital transistor in turn became a switch, and that opened the floodgates of the digital electronics, and then advent of computers. This is all history, but the beginning of that history goes back to the development of a transistor after the vacuum tubes, which were several times bigger, uh, millions of times bigger than what a diode or transistor can be. So these wafers, they have different types of deposition and etching. So the two processes that are used are deposition of different layers of materials and etching out unwanted materials. So those are who are familiar with making of electronic circuit boards, they know that you deposit the certain layer of copper, and you mask certain portions of it, and then you etch out the unwanted portions. And these are the fundamental processes that go into the making of a integrated circuits: deposition of layers, masking the portions of wanted and unwanted portions, and retaining wanted portions and removing unwanted portions by chemical etching. And this is how the making of the chip goes in. So such are the, I mean, to say it appears very simple, but the processes that go into making of integrated circuits are deposition and etching and photolithography for masking purposes. The entire manufacturing process from start to the packaged chip ready for shipment takes 6 to 8 weeks. Of course, this is a time consuming process, although it's a batch fabrication. Several hundreds and thousands of devices can be fabricated at a time. However, the process goes on for several weeks, and it is performed in a highly specialized facility called as fab, or fabrication facility is called as fab. Now, this is an example of photolithography where you have substrate, then the deposition of photoresist, and then there is a mask here. This is a quick look at how these fabrication takes place. So photolithography techniques are used. The substrate is the silicon wafer. Photoresist are the layers that are used for masking, and then you then you create mask, and then you pass ultraviolet light, and there are some opaque and some closed areas, and then you do the etching subsequently, and then unwanted part is removed, and the lift up process takes place. So these are some techniques I am just bringing to your notice, that how IC fabrication goes in. Now this is how a fab looks like. It's called as a clean room. 10 and 100, class 10, class 100, and class 1000 clean rooms they are present, and based on the kind of activities that you are doing, these particular clean rooms are designed. Semiconductor device fabricated in is the process used to create integrated circuit or silicon chips that are present in everyday electrical and electronic devices. It is a multiple step sequence of photographic and chemical processing, as I told you, etching and deposition, during which electronic circuits are gradually created on a wafer made of pure semiconducting material, silicon. Silicon is the most commonly used semiconducting material today, along with various compounds of silicon such as silicon oxide, silicon nitride, polysilicon, etc. Semiconductor manufacturing process, this is a chart which shows you how the size of this technology, which is talked in terms of this length scale of this length scale is pertains to the P and N junctions are there, or the PUL in a transistor. You have got a sink and source, and there is a gate. and many times it is referred to the length of the gate, which is shrinking in size. It was 10 micrometer in 1971, and it shrunk by this particular size. It became 1/10 in 14 years. Then it became nanometers now, in 11 nanometers in 2015. Current size is around 7 nanometers in 2020. So this is the miniaturization in semiconductor technology that is taking place, and that's why we are getting cramping several devices on small area. And that is what Gordon Moore said, that number of transistors per unit area will double every 2 years. He predicted that in 1965, and see, look at the ways thing worked in the several decades after he made that particular statement. So this is a fab. This is the scale of the things that reduces, and uh, that is what the miniaturization that we hear about. Now, again, I will give you a visual for your benefit to understand what is it that has shrunk in size. So if you look at this is a silicon wafer cross section. This is a silicon wafer cross section, and this is an ACM picture, scanning electron microscope picture of the same. Now we all know that there is a semiconductor silicon, and there is a trivalent and pentavalent impurities. So and a transistor is created, a diode is created, and transistor is created, and that paved the way for this particular new development. And then the miniaturization process began. So this is a source, and this is a drain, and this is the gate length, and this reduction of this particular length is miniaturization. The two wells that you can see here, the pentavalent impurity wells, where this doping has occurred here and doping has occurred here, and there is a certain gap between these two. This particular gap has reduced in many orders of magnitude, from micro to nano to sub nano, or not sub nano, but it is a, one digit nanometer length scale. From 10 micrometer to 10 nanometer, that shrinking has taken place, and then the switch has become miniature, and that's why we can have memory size that has reduced, and transistor size has reduced, the device size has reduced. And this is what this particular thing will make you believe that, well, this is all possible. This is the thickness of this is 500 micrometers, that is half a millimeter thickness. So it is many times an enlarged figure of a transistor, field effect transistor. You have got silicon, then this is a P substrate, entire substrate is doped with P, and then the wells are doped with N, and then there is a layer of silicon oxide, which is an insulator, then silicon nitride is there, and then there is you can see here there is a connection between here. There is the well is connected to the source, and this well is connected to the drain, and there is a gate, and the flow of electron in between these is controlled by this gate by applying potential to this gate. So when this potential is analog, this is a analog device, and when this is turned on and off, this is a NOT gate, and a NOT gate is essentially a switch. And the size of switch has, the whole story of microelectronics is the reduction in the size of this particular switch, where when the gate input is 0, you have output 1, and then when the gate input is 1, the output is 0. So a transistor is a NOT gate, and using a NOT gate, several other gates can be realized, and or XOR, and adding half adder and full adder circuitry, and the advent of um, a microprocessor, and then the developments of microprocessor. It's all a history of digital electronics, but it has emerged with the miniaturization of this particular single device, which goes as a building block, which is a building block of electronics. Now, this particular silicon fabrication technology has is established from 70s, 80s. The technology very well established, and it went on shrinking in size. And that is where when electronics was shrinking in size on one side, but the mechanical systems, the sensors and all, they were big in size, several orders of magnitude big in size. So electronics was shrinking, but the sensors were big. And that is where the need of miniaturization arises, because after all, electronics is a field where you can do computational things or signal processing things, but the signal has to be obtained, and the device which is obtaining the signal, which is sensing the signal, if that is big, then the whole system won't make a sense, because everything has to shrink equally in size. For example, you all know the example of a mobile phone. The early mobile phone used to have, the electronics used to be pretty small, although the specs were not so great in those times, but the battery used to be heavy. So it was incompatible situation where a battery body are very heavy, the screen and all, and the electronics is pretty small, sitting on a small chip. That is where the need to miniaturize the battery and increase its power capacity, the rating and current rating, the wattage, and even its life. So people developed batteries which are now pretty small, and still the power rating is quite high as compared to the batteries of those times. So this was a need of the hour to reduce even the sensors and sensing technology. And therefore, an attempt was made to for thinking in the direction of how diaphragms can be fabricated or cantilevers can be built using silicon. And why silicon? Because IC fabrication is done on silicon, so you cannot make tiny devices using conventional mechanical materials and mechanical processes. But you have to think about using this electronic material and electronic processes if you want to enter into making tiny devices at that scale. And I hope you are getting this, because electronics has shrunk in size, and therefore for the mechanical things, mechanical sensors to be developed and made of the same size, you have to use the technology which is amenable, which is already developed, and therefore make use of the material, make use of this processes that are used for IC fabrication. So people started working on this. In 1984, I suppose, Peterson published a paper titled Silicon as MEMS Material. Now then, it is obviously we have to take a look at the material properties. It has got a tensile strength of 7 GPa. It can maintain mechanical integrity at pretty high temperature. Then properties of independent of doping, because electronic properties are because it is a semiconductor, it was preferred. It has a valency of 4, and when you can add practically it is non-conductor, because all its electronics in the outer orbit are sharing electrons with the neighbors, and there are no free electrons. But if the conductivity can be thermally induced or by doping, so that was the preferred properties of silicon. However, now when it is to be made use of for mechanical components, then its mechanical properties become important, and they are not so good, but they are pretty fine, and people started working around this property of mechanical, which is also not as comparable to that of, say, other metals that are used before. There are several other materials that are used in IC fabrication technology for connections that are laid onto the IC circuit, which are metal depositions, or silver, aluminum, gold, chromium, titanium, copper, and platinum, iridium, and tungsten. So these are also these materials that are used in IC fabrication technology for interconnects, especially interconnects connecting devices one to another by depositing the tiny layers of these particular metals. And their resistivity and those properties were of interest for mechanical from electronics point of view. But these were also some of the materials that were used. Besides silicon, above materials are also used in thin film deposition. These are called as thin film deposition because these depositions of a few micron thickness that are used in IC fabrication technology for interconnects and even for micromechanical structures also can be thought about using these. Now, fabrication of MEMS, just to take a relook at the processes that were used, physical and chemical deposition, physical vapor deposition and chemical vapor deposition were the techniques. Patterning is lithography for allowing certain areas and not allowing certain areas. So it is the patterning, and then getting rid of unwanted materials by etching. And there are two types of etching, dry etching and wet etching. We are not going into the details of that, but I hope you have understood that IC fabrication technology essentially makes use of deposition and etching and patterning, and that is how structures are created. Mainly these are planar structures, and therefore for MEMS also you have to think about structures of the same type. Now, to give you just an idea about how a mechanical structure is fabricated, so this is a small presentation slide which can give you how you can fabricate a cantilever. See, look, there is this blue block which is a substrate. On that substrate there is another material which is a sacrificial layer, they call, which is laid down. Okay, all the steps are not here because there are several steps. So this is the substrate, and there is a sacrificial layer because this layer eventually is to be removed. It is to be sacrificed, and that's why it is called a sacrificial layer. Now this sacrificial layer has got a window here. So this sacrificial layer was masked and a small window was kept open and it was subjected to light, and then the portion which was subjected to light became soft and the other surface became hard, remained hard, and then this was etched. After etching, a small window was created here, and this is the substrate. Most of the portion of the substrate has been retained with only a window that has been cut out of it by etching process. A selective etching process is used. Then another material, say polysilicon, is deposited. Now this material is deposited again on this with unwanted portion masked, and only the wanted shape is deposited here, and some material seeped through, went under this, and it got attached to the base. Meanwhile, again, by using another etchant, the sacrificial layer now is fully etched out. And that is how, when the sacrificial layer is etched out, what you got is a freestanding cantilever beam. I hope this must have given you a brief and quick idea about how it is possible to create planar structure by merely deposition and etching and selective etching by subjecting to what is known as photolithographic techniques and masking and unmasking, and using different types of etchant, you can create a cantilever beam like this. See, this was the substrate. There was a this was a sacrificial oxide layer, and then there was a window that was created, and then another layer which was deposited, which conformal deposition took place. So it went underneath like this, and then this unwanted layer in between again etched out, and you got a freestanding structure. This is a cantilever. If you have an electrode here, then this particular will be a parallel plate capacitor, and if a parallel plate capacitor, when subject to displacement of one of its diaphragm or cantilever plate or upper plate, then there will be a gap change, and this gap change will create a change in capacitance, and there will be signal available, electrical signal available. Or you can deposit materials such as piezoelectric or piezoresistive material, film can be deposited on this, and that also can give rise to signal when it is subjected to mechanical deformation. So I hope you might have understood or got some insight into how it is fabricated, how transduction principle can be incorporated, and how it can electromechanical system can take birth by this particular surface micromachining technology. Now, MEMS has gone a long way. For the last 20 to 30 years, it has made a huge progress, and several other materials, because as the technological demand and need and market drives all these developments, the newer materials have come in. So remember, at the time of the entry, when MEMS entered into electronics, there were constraints of material that you have to use silicon as the base material and some other derivatives of silicon, polysilicon, silicon nitride, silicon oxide, so on and so forth. Those were limitations, and you have to use only a few uh, etching and deposition are the processes that were at the disposal of the researchers. But when they came up with inventions and developments of various sensors, and then the possibilities grew up many folds, and then new materials were also became amenable to these inorganic materials such as high temperature materials, silicon carbide, uh, silicon and germanium alloy, and then diamond, because it is electrical conductance and mechanical toughness, because again properties pose limitations, and therefore one makes attempt to overcome those limitations by using different materials, but the processes must allow making use of those materials, and that became eventually possible. Then laser micromachining, deep reactive ion etching, focused ion beam etching, chemical and mechanical polishing, permanent magnet and electromagnetic materials, and rapid prototyping. These are the several new processes that were adapted by IC fabrication technology, especially for MEMS fabrication. Silicon, organic materials such as elastomers, polymers, chemical vapor deposition with pyroline, and electroactive materials. New materials, they were welcome in this particular field of IC fabrication technology with the advent of MEMS. MEMS benefits and applications. Now you have got some glimpse of what are MEMS, what are mechanical devices, how they are integrated and fabricated on silicon wafer, and we will see further few more things. But before that, this advantage of smaller size, batch processing, so you can produce them at low cost, uniform production, distributed device placement. So this is a wafer, and these are the tiny patches that you see are the individual devices that are fabricated at a time. So that's why it is called as 4,000 die per 6-inch wafer. That means on a 6-inch wafer, you can produce 4,000 dies or individual devices, which can be later on cut into pieces and packaged. Applications such as accelerometer, gyros, pressure sensors, and actuators such as tweezers, micropumps, motors, and RF radio frequency switches. So these are some of the enabling, MEMS is being an enabling technology. This is how the commercial aspects of it, they need to be understood. Fabrication, fabricated through surface micromachining process, and this is, we have seen this. Now this is again a small illustration that will help you believe how the process flow goes. You have design the devices, free form geometries and 3D solid models. You can design, you can do the analysis, coupled electrical, mechanical, fluidic analysis can be carried out. So you can use different computational tools to design and analyze the devices, and then you can decide the dimensions, finalize the dimensions of the device, and then you go for fabricating those devices on silicon wafer. Several such devices can be fabricated on the wafer, and then the patches can be diased, and then one patch is a single device that can be packaged into what we generally call as integrated circuit chip, but the chip is there inside, and these are the wire connects, and these are the legs of this IC, and the device can be given power, external bias, and the signal in and out can take place, and this is the final. So the sensor will be sitting inside this. The mechanical sensor will be sitting inside it, and it will be provided bias, input and output. and it can be made use of, and it can be subjected through a small window. Probably it can be subjected to the if it is a microphone, you can have an opening there too, so that the acoustic pressure can act onto it. So this is how birth of a mechanical device and appearance like that of an integrated circuit chip that will take place. So MEMS design and fabrication, a quick view of this: design, analysis, and fabrication, packaging. Design, analysis, fabrication, and packaging takes place in the way it is seen on the screen. So this is another illustration of the same thing, because packaging finally is very important, because this device has to be protected from the environmental hazard and therefore it has to be packaged well. So packaging itself is an area of research and technological development. So this is again finally how a device from a wafer diced and packaged into an integrated circuit, and then it becomes a part of some uh, uh, bigger circuitry, and then it will go and sit into the uh, airbag system of an automobile, or skid braking system sensor of the automobile. See, we are all familiar, we are all using this technology. All of us have got a car with a airbag, and that airbag system has got an accelerometer which senses the limiting acceleration when the car hits an object or there is a heavy impact the car undergoes. That time the acceleration threshold is crossed, and when the acceleration threshold is called, the sensor senses it and it gives signal to the actuator, where the airbags are inflated within seconds, and our lives are protected. So similarly, anti-skid braking system, where the skid is sensed by a gyro or an accelerometer, and the deviation from the course of the car path can be sensed by the sensors, and corrective action can of braking against the skidding of the car can take place. And these sensors are now become affordable, and therefore they are being deployed in most of these automobiles. So MEMS has got tremendous applications in automobiles. BioMEMS is another field where MEMS is coming in a big way. You have several types of sensors developed. Uh, you have implantable blood pressure sensor developed by CardioMEMS, where this blood pressure sensor can be implanted into human body, and you have transmitter receiver, or you can have some variable device which can get the signal readout is there, and you can continuously monitor the blood pressure, and several other vital parameters of human body can be monitored. Or even you can have a drug delivery system that can be deployed in the body of the patient, or a patient can wear a device where the blood sugar can be monitored, and a tiny uh, uh, amount of insulin can be injected by a micro needle and a micro pump into the subcutaneous cells of the human body. So there are drug delivery systems that are developed, which are pretty small, and which have got sensors, actuators, and controllers sitting in a small uh, device of size of a watch that we wear. And there are several other stimulators that are needed for geriatric patients who have difficulties in movement of joints and muscles, and even pacemakers are become the uh, devices which have emerged with this MEMS technology. So smart muscular prosthetic devices, they are also there. Bladder stimulators are there. People have problems with urination, and for such patients, bladder stimulators can be implanted in the body of the patients. So this is really an enabling technology, and BioMEMS and medical field, biomedical field has given a tremendous um, uh, uh, scope for development of several sensors and technology and economy. Uh, Driving force has been there for this particular technology. Another important area is condition monitoring. Condition monitoring, you might have heard that the way the health monitoring of medical, in the similar fashion, you have to monitor the health of plants, machinery, equipment, structures. These days we heard that a bridge collapsed, and there should have been a means of monitoring the health of the bridge, and that is quite possible by deploying several sensors onto the bridge and getting the data of vibration, displacements, and cracks that are existing in that. And therefore condition monitoring of human or living beings, similar to the condition monitoring of plant, machinery, and equipment is also uh, made possible with the advent of these sensors. Now, this is another small example because this particular technology is not confined to any particular field for its development as well as for its application. I will repeat that MEMS technology is not confined by any discipline. You might have heard by this particular discussion today and last 2 days that there is no barriers of mechanical, electrical, civil, and IT, and computer, and instrumentation and control. All are working together in unison, and in fact engineering is what fundamentally goes. Science and maths is what is the governing principles that go into making of these things. So in civil engineering also, you have these reinforced concrete structures, and you never know what is the health of this particular structure. However, it is now possible to deploy different types of sensors on the surface of this particular concrete, and you can have a small hole drilled into this particular concrete beam where a wire can go and reach the steel rod, and then you can apply a potential, and some of these sensors can receive signals from there. So there is a reference electrode, this is a counter electrode, then this is a guard ring where these sensors are fitted, and then you have a sponge where this impedance matching purpose this particular is used on the surface of this particular concrete, and you can get various kinds of signals, and on the basis of which the health of the structure can be assessed, and that will help us in avoiding catastrophic failure such as sudden breakage of these structures, bridges, and big buildings, tall buildings, and all. So this is an important boon for us for acceleration, acoustics, and strains and corrosion sensors are being developed by MEMS technology, and they can take care of even civil structures, mechanical structures, or mechanical machines. You can monitor the health of the machines by monitoring vibration and noise, and you can take preventive maintenance activities can be carried out. Predictive maintenance activities can be carried out. That means you can predict the onset of failure and avoid the sudden failure or stoppage and thereby losses incurred due to that. So you can schedule the maintenance activities by knowing or monitoring these health of these structures by using MEMS sensors. These are some of the applications in automobile. There are several sensors that are used in automobiles. You name the sensor and it is there in an automobile. So automobile is a field where we only saw for the safety point of view, there is a airbag and anti-skid, but there are several other things that needed to be, parameters that needed to be monitored, sensed, and controlled in an automobile. Even the engine efficiently running an engine requires monitoring of several parameters. Inertial navigation sensors are also there in the automobile to avoid the skidding of the automobiles or rolling or overturning of the automobiles in different environments. Now, we have come more than halfway down our presentation by taking the review of this particular micro electromechanical systems. I hope you are with me. Hello.
Yes, sir.
Yes, sir. Yes,
Yes,
sir.
sir.
Yes, sir. Yes,
We are
sir.
listening to you.
Yes, and I hope it is not getting monotonous or boring, because I have been speaking all alone without you people uh, in picture. I feel like I'm talking to a wall. So now we are going to see a device that will create more interest in your mind. How a typical device, because now this is all several pictures I've shown you, but you would like to see a device, actual physical device. What is its size, how it moves at that scale, and I'm going to show you in the end of this particular presentation. I have chosen Gyroscope as one of the devices, but before that, some of you probably must be thinking about undertaking research in this challenging and emerging area, and therefore you must be knowing what are the things that this particular engineer has to do, where he has to start, what are the devices and tools used for designing, and in what way it is different from the conventional design. And several other questions might arise in your mind, and it's a being interdisciplinary. Do I need to know electronics? Do I need to know mechanical? Because a person from mechanical background may feel that, do I need to know electrical and electronics? A person from electrical background or electronics background may have a question in his mind that, do I need to know mechanical things and resonance of a cantilever beam, or the stress analysis of structures and all. See, I mean, for interdisciplinary research, you need to have an open mind and a willingness and readiness to look into other discipline. At the same time, explain the phenomena and ideas and principles and theories of your domain to the person that you are working with from other domain. So this particular interdiscipline exchange of ideas and thoughts and knowing from other discipline and getting the other person know from your discipline, this is something you should be prepared for, you should be ready for. And you should start this from your own institute, because as you know, when you work on small projects such as a making of a robot, you know that you have to get hold of an electrical person for choosing the right motor, the servo motor or stepper motor, and then you must find out what is the torque required, and then you have to get into the mechanical domain and see what is this friction, how much friction will have to be overcome, and what is the leverage, and what is the torque that I will need, and whether my motor will be able to negotiate that particular torque. So this particular thought process begins when you start working with interdisciplinary team members. You need to know what is the sensor available, and what is the how the sensor needs to be mounted. If I want to detect an obstacle, an RF sensor is required to be used, or a ultrasonic sensor I want to deploy, and then what is its specifications, what are its input and output signals, and how the signal processing is to be carried out, and what electronics is required for that. See, once you enter into this particular interdisciplinary domain, you have to be inquisitive, you have to take some extra efforts, and I mean, relate. It's not that the things are very different. It's all about fundamental science and maths. Mind well that we are all basically persons with science and maths background, and the disciplines are merely a convenience. The disciplines have been created only for convenience, and that need not be in any way any limitations. And in modern times, certainly it shouldn't be, because we are talking about Internet of Things, we are talking about industry 4.0, we are talking about deploying sensors on mechanical systems, we are talking about uh, wireless communications, where there will be a transmitter and there will be a receiver sitting at distant place, and the data will be gathered, and then the computer will process the data, and the data needs to be analyzed. So you have to learn how to process this data so that you can get some meaningful interpretation and information or knowledge out of that particular data, and so that you can further make use of it for decision making or whatnot. I mean, to make things better. So this is something you have to give a serious thought to when interdisciplinary working. So now we'll take a look at how the devices are analyzed, the MEMS devices. So these are some of the devices that I myself did analysis on during my PhD at IISc Bangalore. At this juncture, I am going to give you another example of when I was talking just now, I was talking about the discipline. And tomorrow you are going to have a renowned speaker, Professor Rudra Pratap, who was my advisor at IISc Bangalore. And you will not believe, Professor Rudra Pratap is a graduate civil engineer, and he is one of the founder members of MEMS and nanotechnology in India. And there is a Center of Nanosciences in IISc Bangalore, which is a huge world-class facility. And Professor Rudra Pratap, who comes from civil engineering background, who eventually did his MS and PhD from Cornell in nonlinear dynamics. And he came in 1996 to India, and he had that willpower and vision in 96 to work in the area of MEMS, when there was hardly any facility available in India. There was no facility whatsoever available in India in 96 when Professor Rudra Pratap started doing work and giving projects to his students, undergraduate students, and then rather postgraduate students. And then I was one of the early PhD students who joined him in 2003. And there was hardly any facility, and we were wondering whether we will be able to do anything, any research where the facilities are not there. It's going to be all theoretical. Although I did my PhD in the theoretical aspects of MEMS, later on in 2008, 9 and 10, he came up. So it took him more than a decade to set up a world-class facility. 15 years he spent a considerable amount of his lifespan in IISc for developing this Center of Nanosciences, along with his colleagues in IISc and some more colleagues from IIT, IIT Bombay and Chennai. So remember, it takes a lifetime to really make big difference and to have big dreams, to fulfill big dreams. You have to sacrifice a great deal. And therefore, I am extremely, in the context of discipline, I was referring to Professor Rudra Pratap. Now, he is comfortable with his fundamental physics, chemistry, and maths. And that's why he could venture into, any field for that matter. The structure, these are the structures that you are seeing on the screen. This is a microphone made out of MEMS, and this is a tuning fork gyroscope, which is a plate-like structure here, and there are some beams you can see here. So these beams and plates are something that came from civil engineering for Professor Rudra Pratap. But along with that came several other things, that in between these two plates, there is air, and the small gap between these two plates is of the order of few microns, 2, 3, 4 microns. It will take you a few days to understand what is meant by 2, 3 microns and gap, and what could be happening in such a small gap. But in such a small gap also, there will be millions of air molecules that will be present there. And when this diaphragm oscillates, this air will try to squeeze out of this particular gap. And in doing so, that air can offer what is known as a damping, or air can even get entrapped. And if the air gets entrapped in the small gap between the two transversely oscillating substrate and the diaphragm, then there will be entrapment of air, and it can act as a spring. Compression and expansion of air can take place. And I did my research in studying the behavior of this air in the gap, in the small gap, which is called as a squeeze film. the air gets squeezed in the, a film of air gets squeezed in the gap, and it offers damping and stiffness to the structure. And I developed some formulae by closed form formulae for analyzing MEMS devices. So, I mean, it was not stopping for me that we do not have a fabrication facility available in India, and how do I venture into this particular field. So we took this risk of doing research into MEMS, and eventually I ended up developing formulae for estimating the damping and the stiffness that is exhibited by a film of air between the oscillating structure, where you develop a MEMS microphone. So I hope this particular experience of mine must have given you some thought about that. Even if the field is huge, it has got several branches that are associated with it, branches of engineering and disciplines, various disciplines. When you start working, you end up working into some aspects of this particular big technology. That is one thing that has to be kept in mind. You eventually work onto some aspects of it. However, while doing so, you come across a bigger picture of the technology also you get acquainted with in the process. So this is something I would like to share with most of the young faculties that are attending this particular session. So it takes a while for you to venture into the field and then know several aspects of it, and then pick up the areas of your liking, and where there is a scope for undertaking further research and development. So it may take, say, maybe 1 year for you to identify the specific area that you would like to work on. So this is a substrate. Again, as I told you, this is a silicon wafer. This has been etched out from the bottom, and then there is a deposition and all, and there is a diaphragm over here, and this is a parallel plate capacitance. And then this parallel plate capacitance is something that is now acting as a microphone in our mobile phone. So remember that you people are all using this MEMS technology in your mobile phone that is sitting in your pocket all the time. So MEMS is not new to you. Hello, there is some.
Yeah, there is some noise. Yeah,
Yeah.
Professor D. Narasimha, please mute your.
So, just jokingly, I would say that my research topic was confined to this small gap and these perforations that you see underneath. So this was the space of a few hundred micrometer. That was the area of research for myself, where I did my squeeze film analysis, where I solved Navier-Stokes equations, and where I developed some closed form formulae for the air and structural interaction and the behavior of air in a small gap between these oscillating MEMS structures. Now there are some perforations that you can see here, and in the structure also there are some perforations. Can anybody tell me why these perforations are there? These are some plate-like structures that you can see here. There is one here. There is a microphone. Here is the gyroscope. There is a plate here, and there are 4 beams here, which are anchored here. And there are some tiny holes on this particular plate. Can anybody tell me?
To reduce the weight?
No, not to reduce the weight. It is the process.
For heat transfer?
No, because this is a device not working in. This is a dynamical device, structural device, not having any thing to do with weight or even heat transfer. But the manufacturing process or fabrication process you have to think about. This is a suspended structure, remember. And the 2 processes that are used are deposition and removing unwanted material underneath the structure, etching. So you can see here, if it was a solid plate, then the etchant has to go from the sides. The etchant has to go from sides. Now the gap between the substrate and this particular plate is few microns. So the etchant, if it is made to go from sides, then it will not reach till the center. The etchant will etch out some portion near to this edge, near to this edge, near to this edge, near to this edge. But the material which is underneath the plate at its center, it will be extremely difficult for the etchant to reach there and etch out. And therefore, these small pockets are created, and the top electrode surface itself is having a perforated structure like this, because these holes are etched first, and through these holes etchant goes inside, and the layer underneath that is etched out. So it is the requirement of the fabrication process. For the planar structure, see the dimensions. If you see here, this is the 200 micron scale. 200 is this much. So this particular plate that you are seeing on the screen, it takes a while, I told you, is approximately 400 micron by 500 micron. The plate that you are seeing, now how much is 400 and 500 micron? It takes a while. Your hair is pretty big. Here is 100 micron. So 400 micron means this particular length of the plate is equal to the thickness of 4 hairs. 4 hair put one beside another, the thickness will be as that of this particular plate. And the gap between this plate and the substrate underneath is only 1 or 2 micron, which is 1/100th of the thickness of hair. लक्षात घ्या, ह्या प्लेटच्या आणि सबस्ट्रेटच्या मध्ये जी गॅप आहे, the gap between this plate and the substrate is 2 microns, 3 microns or 4 microns, which is a very, very small fraction that of a hair. And therefore, to be able to get a freestanding structure, a structure which is separate from the substrate, which is hanging from the substrate on these anchors. These are the anchors. Shall I go back to the earlier picture that I showed you? This one. Now look at this. This was the sacrificial layer. Now this sacrificial layer has to be dissolved. So that means the etchant has to go underneath this and etch out. Now this being a cantilever, there is no problem. But if this were a plate, then the etchant has to, and this particular gap is very small. Remember, this particular lateral dimensions are several hundreds of microns, whereas this particular thickness is only 2-3 microns. And therefore, the etchant has to go laterally underneath the top plate, top layer rather. It will become a plate once it is released. It is called as release. The MEMS structure is released. See, this is the released cantilever, because now there is no material under it. It has been etched out.
Sorry to interrupt, sir.
Pardon?
I'm sorry to interrupt.
Yeah.
We have next session at 11:30. So if you can
Yeah. Certainly. Only thing is, I was asking you that small question, that these holes are for sending the etchant, and then the etchant will remove the material around the hole, and then the entire material will be removed, and then this particular plate will be released, and it will be freely oscillating. These beams are also released. These beams are also released, and this particular end of the beams is anchored, and therefore this particular plate can now oscillate in its plane, or it can oscillate out of the plane. So I hope you understood some insight you must have got about the size of the things. Now at this juncture, I will be happy to know if you understood or got some feel of the size of the micromechanical structure. This is the real structure. This is not a photo. I mean, this is a photograph of a real mechanical structure that is fabricated on a silicon wafer using polysilicon, and then the gap underneath is created by etching the material and under it by sending the agents. Then one more thing you can see here, because unless you do few observations here, you won't be able to appreciate that these are comb-like fingers are there. This is a fixed comb, and this is a comb fingers on the plate, and these combs are interdigited. So there are combs from this side, and there is a comb from this side, and these fingers of the comb, they are interdigited. One on the plate which can oscillate, and another is fixed here. So this is provided for electrical excitation, and this plate can be kept oscillating. That I will come to once we are. So I will have to move fast now. Okay, so this is the analysis of MEMS. If you don't want, I can skip this, but I will just take 1 or 2 minutes. So this is the microphone, and you need to do the analysis. So some of you may be wondering what kind of analysis is. So multiphysics or coupled field analysis is required to be done, and you need to solve partial differential equations as well for doing the analysis of a tiny hardly 1 square millimeter by 1 square millimeter microphone, which has a diaphragm. There is a air, there are these perforations, and there is acoustic pressure acting on this, and there is electrical potential applied between these two electrodes, and there is a electric field or electrostatic force that is acting, which is half v square upon epsilon to epsilon, half v square upon epsilon. That force can be acting there. Then there is a air also can be undergoing compression, and it will be rushing out of that. So there will be pressure of air underneath it. And so, I mean, there are 4 domains interacting: the acoustic domain, the structural domain, because this is a structure, a diaphragm, then the fluid domain, and then there is an electrical domain. So 4 domains are interacting in the functioning of a tiny microphone that is sitting in your mobile phone. And you can do this analysis in any of the finite element analysis software or finite volume analysis softwares based on the rigor of analysis that we are interested in. So, but don't get afraid of this. There are these tools, and ANSYS Multiphysics can provide facilities for modeling these devices quite well. You need, there are 2 options. Again, you need not have to do full 3D analysis by solving partial differential equations, but a reduced order model can be made by making a parallel plate approximation of this particular model. And you can have a mechanical structural model combined like this, where you will have a plate oscillating which has got its own stiffness, and then there is an air underneath that can also offer damping and stiffness, which I worked on. And then you have this interaction. You can analyze these dynamical equations. We are all familiar with the second order differential equation for the oscillating plate, which is subjected to some stiffness. And then there is an electrical circuit, because this parallel plate capacitor is a capacitance and a resistance which is given a potential or bias voltage, and therefore this is an electrical capacitor also. This is a mechanical diaphragm and electrical capacitor, and where they have a coupling, the coupling is in the form of this displacement of the capacitance. You know, capacitance is function of epsilon A by D, or the gap, and this air gap or this W variable you get by this mechanical analysis, and this W variable causes the change in the capacitance, and the change in capacitance gives rise to change in the charge or current in this particular circuit, which is transduction. So you can have 2 separate models made, and you can do reduced order modeling to make your life easy, and you can solve ordinary differential equations. One more thing I will bring your attention to. The other day, Professor Anand Suresh has mentioned about the negative spring that comes into picture for the electrostatic spring, because there is an electrostatic force, and as these plates come closer, there is a snapping of the plate that can occur, because it's kind of a non-linear force that comes into picture when because of the electrical bias, and therefore this electrical spring also comes into picture. Moreover, conventional mechanical damping and mechanical spring, they come, but beside that, this is BA and KA are the damping caused by air and the stiffness of the air. So this is how this is a reduced order model, but all the properties that are exhibited by a fluid and electrical domain, they have been incorporated in this mechanical equation. And this is the acoustic pressure, or acoustic force rather, that is acting. This is the mass of the diaphragm. These are the dampings. One comes from the structural damping and another component comes from the air damping. Then these are the stiffnesses, a structural stiffness, and then the air stiffness if the air gets entrapped. And there is a electrical spring force that act weird here, and it can have a negative as well as positive value based on whether there is a attraction or repulsion that is taking place when you apply a changing AC voltage, especially when the signal is acting. There is a increase as well as decrease in voltage, and there will be a positive and negative spring effects that will be seen on either side of the reference position of the diaphragm. Now, this modeling can be done using devices such as Simulinks. These dynamical equations can be written in state space, and you can use, many of you must be familiar with Simulink, and you can do Simulink models and solve these equations. So, I mean, there is a scope for research, and usually in research, we get into development of sensors, and then you need to model those tools and then analyze their properties. So this is these few slides will give you a idea about what kind of analysis that goes into. Now give me another 10 minutes to complete this particular example of a MEMS gyroscope. Now, gyroscope is a device that is familiar with mechanical engineering students. When there is a rotating wheel, and when the rotating wheel is continuously rotating wheel, when its axis also undergoes a rotation, undergoes a rotation, like for example, you are driving a car, the car wheels are rotating around its axis, and when you take a turn, then the axis itself is undergoing a rotation. And when this kind of interaction occurs, you experience what is known as a Coriolis force, which acts which exhibits a couple around the third axis, and that is called as a Coriolis acceleration. And this particular Coriolis acceleration, or even it is a gyroscopic couple, it is called as, it is a phenomena that is experienced in navigation, and there is a counterweight that is used to measure and balance these forces. However, in this particular application, we are using this particular property of Coriolis acceleration for measuring the rotation rate. So when there are several applications where you are required to measure the rotation rate and or respond to the changing rotation from forward, backward, or there are roll, yaw, or pitching actions that even the games that you play on a mobile phone, where you can make motions in such a way that there is a sensor which can sense the rotation that you have given or carried out to the device, or through the keypads in the forward, backward, and left and right directions, where these rotation can be sensed and some action can be initiated corresponding to that. Now, just to give you how this tuning fork gyroscope is in another example of that, where the tuning fork you are all familiar with. This is a tuning fork, very much familiar, all of us are. The two prongs of the tuning fork are kept oscillating in the plane like this. The two prongs of the prongs of the tuning fork are kept oscillating like this. And when these two prongs are kept continuously oscillating by applying some kind of bias to AC plus DC bias can be given. And so the comb fingers that I showed you that were used for this purpose only, the two masses are kept oscillating. And when there is a rotation is given to this particular entire assembly around another mutually perpendicular axis, then the two masses they found to move like this. Those which were oscillating in plane, because of the rotation given around this axis, the masses will fly in and out like this. So this is the response or the a sensing that will take place. The masses are kept driven into this plane. Can you see the slide? There was sudden.
Yes, sir.
Yes, sir.
We
Yes,
can
sir.
see
Yes,
the
sir.
slide. Yes, sir. We
Yes,
can see
sir.
the slide.
So just hold on for another 5-10 minutes. Okay.
Yeah. I already, sir. Professor Akshay Naik from IIC Bangalore is on the board.
Okay. Okay.
So if we can finish in 5 minutes, so we can start in a very time. So we can
Okay.
take some questions after like 5 minutes.
Okay. Okay.
Okay.
So this is the circuit. Then this is simulating model that you can do for the resonating. So this is the ANSYS model that you can see here, where the masses are kept in anti-parallel mode. That means they are moving apart and coming closer, moving apart and coming closer, and they are kept driven in this particular manner. And when a rotation is applied along this particular x-axis, when rotation is applied along x-axis, then these masses on account of Coriolis force, they move out of plane like this. And when these masses move out of plane, there is a change in the capacitance underneath, which is proportional to the rotation that is given around the x-axis. Around y-axis, they are kept oscillating. When rotation is given as a rotation rate is given along x-axis, the masses fly in z direction. That is the response to that. So this is how the sensing takes place. So this is an actual device of this MEMS. Now I will show you a few videos of actual device. Just check whether you are able to see that or not. Two, 3 minutes. So I hope you can see this.
Yes, sir. Yes, sir.
So this is called as a drive mode. I hope you can see even the comb fingers. The fixed cone fingers are not there in this particular animation because this is done in a Convener software, but I will show you the fixed combs also in actual device. So the device, the two parts are kept oscillating like this. I hope I will just recall in quickly that this particular structure is of 400 by 400 microns. This particular plate is hardly half millimeter by half millimeter size. The gap between this plate and the substrate is hardly 2-3 microns. There are these beams and these are the anchors. So I hope you are familiar with the terminology now. These anchors, the beams, the plate, and the drive mode that it is kept oscillating. And when this particular structure undergoes a rotation around a second axis, say y-axis here, it is now oscillating along x-axis. And when rotation is applied along y-axis, in response to that, the Coriolis force make it oscillate out of the plane in z-axis. That I will demonstrate you quickly, and then I will show you actual device in next minute. So this is the sorry, this is not the one I was looking for. out of the plane. Now in this video, you will see the response. This is how out of the plane. And when this particular response, there is a gap in the capacitor, gap changes. The change in the gap of the capacitor will is the that is how the transduction takes place. The signal is available there. I hope you are getting this. The rotation that was caused, the drive mode was there in plane, and the rotation was given, and the response due to Coriolis force or acceleration is out of plane displacement that has occurred, because of which change in capacitance will take place, and that is how the transducer is realized as a tuning fork rotation rate sensor. And this particular sensor has got several applications in gaming devices and in inertial navigation. And now I will show you the actual device physically, how it looked when we developed it in IISc Bangalore. Not in IISc, in those times the facility was not there, but it was fabricated at other facility, and then we tested it in our laboratory. So this is the real device. Probably in your lifetime, first time you are seeing a MEMS device on silicon substrate, which is, see, these are the comb fingers. This is a pad where these this excitation or bias voltage AC is given, because of which this plate is kept oscillating. This is a needle where this bias voltage is applied here. Another needle is not seen here in the picture. So I hope you will appreciate this particular thing. So this is the actual device. The small particles that you see in the screen, these are debris, and that's why these devices are required to be kept in, fabricated and all treated in a clean room, and they need to be packaged. Otherwise, they will be. And this particular space that you are seeing on the screen is hardly a couple of square millimeters. The entire space that you are seeing on the screen is hardly a couple of square millimeters, in which this plate is a fractional square millimeters. The plate is a fractional square millimeter. This is a there is another plate here. There is a reason why two masses are used, because of accidentally handling and all, or any other external acceleration, both these plates will experience the same acceleration. But since they are moving in and out, the change due to other effects will get cancelled, and that's why this twin pair of devices is used. So with one more small device presentation, I will close this in next minute. So this is the device again that can be seen here. See, look at the debris, because we were not so aware about the handling of the device, and that's why the debris there. These are particle 100 times smaller than the dust particle that we normally see, but still they are appearing so big here in this particular video. So this is how the device is. There is a life that has been brought in the device, and now these are the pads from where the bias can be given and taken out, the signal can be taken out, and the electronics of this particular device will be sitting next to it. And that is how the realization of micro electromechanical systems on a single chip. You will have the mechanical moving structure, and you will have the electronic circuit which will be doing the signal conditioning of this device, and that will be packaged in a small IC. So I hope this might have given you some idea about what MEMS is all about, and thank you for being so patient for so long, and I have concluded my session here. Thank you for giving me a patient listening.
Thank you, sir. So quickly we can have one or two questions from the participants, and then we'll move quickly to the next session. So any questions from the participants? Yes, Professor
Sir,
Charudatta.
yeah, the simulation you have talked about is done in the MATLAB software, or which software you use? That was.
Yeah, in fact, the full 3D analysis where the PDs are solved was done in ANSYS and Convener, but you can do a reduced order model where lumped parameters are extracted. As I told you, mass and stiffness and damping coefficients, they can be extracted by doing extensive analysis, and then you can do the modeling of the dynamical equations using tools like MATLAB Simulink and circuit simulators. They are there. So MATLAB can be very well used. I have used the Simulink, MATLAB Simulink only.
Thank you.
Any other question?